There is an infinite amount of energy locked in the vacuum of space-time. Could we ever use this energy? This is a very interesting article. I enjoyed reading it. I mean, seeing how other people think. The first sentence there, here's the first sentence of the article. There may be an infinite amount of energy locked in the vacuum of space-time. The key word here is maybe. So people are not sure. I say there is a definite yes to it. There is an infinite amount of energy. And I'm going to explain why as we go along in this short video. Vacuum energy, this is the energy underlying everything. The one who says the energy underlying empty space, 0 point energy, where it's very low, the energy, there's nothing moving. But there is evidence that there is a lot of energy there, I mean, where does everybody think virtual particles are coming from and all this virtual stuff in people's calculations? I mean, it's virtual, it's not real, but it is real, There's an infinite amount of stuff happening out there. And, there's, quantum theory, quantum electrodynamics suggests that there could be an enormous amount of energy out there, but cosmological observation suggests if it's there, it's not that much. But how are they making these cosmological observations? With what instruments are they using? We are talking about an enormous amount of energy, but at very low levels. There's very little kinetic energy there, of these underlying fields, these underlying quantum fields, in space or near zero temperatures. There's very little energy. Our instruments have difficulty detecting neutrons, So who are you trying to convince by using a telescope to look for this underlying energy and then saying cosmological observations do not confirm this? They're not supposed to, because we don't have the instruments. But we have our minds and we have logic and we can ask what is happening, These fluctuations are based on Heisenberg's, in quantum electrodynamics, are based on Heisenberg's principles, So, but these fluctuations would be so low. We're talking at near Planck scale, We don't have those instruments, but the energy has to be there. I mean, take quarks, how they're bonded together by gluons. As you pull that gluon away, as it's pulled away, there's, the gluon flux, gets more energy. Where is that energy coming from? And then when it splits, you find mesons. A pair. Two. So, where does everybody think this energy is coming from? From thin air? From nothing? Oh man, please. We are all people who believe we have a mind, You cannot then tell somebody with a mind that when these gluons pull away, suddenly this energy came from nowhere. That's an enormous amount of energy. And to mess around with these quantum fields, you need that amount of energy, the strong nuclear force. It's so much, and only what we know, it's only the strong nuclear force that can mess around with this energy. But it's not only the strong nuclear force. Let's look at magnetism. It leaves the magnet and travels in a linear line, and it will be explained from one point to another. But it's losing energy all that way, and then it's gone. Where did its definition go? To nothing? This shows how magnetism declines. This is energy, and this will specifically be E1. But this is energy, and this is distance, and this distance is a multiple of the Planck length. This D here is a multiple of Planck length. And this OI is how much is lost per each multiple of Planck length. This is how much energy is lost, and this EI is the initial energy of the magnetic wave as it leaves the electron. So this is all energy here. All this is E. So energy of magnetic energy, we can call it E, equals EI minus OI D, because each electron would have a unique, not unique, but there'll be a bandwidth of how much energy can release. So sometimes an electron will release energy from here, sometimes from here. So the distance depends on how much energy started off with. You understand? Sometimes it will be like this. So what you are measuring will be a summation of all these energies when you put, anyway. So this energy has been lost. Where is it going? Somebody could argue very well it's energy that came with it from the electron. So, and it's going, but it has to be going somewhere. It can't just disappear. But then there's the structural energy, ES. This thing cannot go below ES. The structure of the thing, that gives it its definition. We know this is a magnet. We know this is an electron. We know this is a photon. Once that structural energy is gone, it ceases. So where does all this energy go? This energy is going to the underlying energy place. We are now beginning to understand the actions of what the Greeks called ether, what different cultures have given it different names. People who studied light and looked at light gave this thing names. So we're understanding, you can call it many quantum fields, but the summation of those quantum fields is the ether. And all that energy is the ether. And when you get an event like a gluon, enough of it, in the past, something triggered it. You get a big bang. All that energy turns into something. You understand? About use, I don't know. Our closest thing is to how do we break up quarks and use that energy? How do we pull quarks apart and stuff like that? But it's better we look at the cosmic rays, man. It's easier, it's fission. We have the fission technology. That's an easier thing to do.